Chris Demers. I'm head of digital and data at Skellig, and today we're talking about process analytical technology. To set the stage for our discussion, I want to talk about something that I learned quite early in my career, which is that biology is unbelievably complex, and we know surprisingly little about it. So I spent the better part of 8 years in the field of tissue engineering trying to reverse engineer this. This is a diagram of early spinal cord development. And here we have this fundamental process of development, something that evolution worked out eons ago. And yet we haven't even begun to scratch the surface of how the complex interplay of diffuse signaling factors and physical factors all work together to create the multitude of neurons that make up our spinal cords, including motor neurons, which innervate our muscles, and they can only be found in a very specific location in the developing spinal cord. Now let's bring it back closer to home and imagine you're working in bioprocessing or biomanufacturing, and you have a complex unit operation like a bioreactor. And your job is to make this process repeatable so that hopefully you produce the same product every batch. You've got gases flowing into your system and you're measuring things like pH and dissolved oxygen in real time. And you've got an agitator that's keeping everything well mixed. But how do you know how many cells are in the bioreactor? Or how much food is available for the cells? Or how much waste they're producing, which might indicate cell stress? To answer any of these questions, we have to take a sample of the bioreactor and we have to run it on an at-line piece of equipment. Maybe it's a ViaCell, maybe it's a Flex 2. But there's a problem with this approach. For one, it's reasonably time consuming, and so we limit this to once a day. This means that over the course of a 14 to 20 day mammalian cell culture process, we only get 14 to 20 data points. 14 to 20 data points for a complex process that we know surprisingly little about. That's extremely low fidelity data, and it would be basically impossible to do any machine learning or any type of advanced analytics on this data set. And the second and perhaps even larger problem is that when we take a sample, we introduce the risk for contamination, and that could cost us the entire batch. What if there was a way to measure the cells in the bioreactor, or how much food is available for the cells, or how much waste they're producing? An inline probe that's no different than the ones we use to measure pH or dissolved oxygen. So this is the field of process analytical technology. These are inline, at-line, or online sensors that can measure the most critical process parameters in biomanufacturing. So now instead of getting 14 to 20 data points in an entire run, we're getting 20 data points every 10 minutes. That's 14,000 data points in a run. That's the type of rich data set that we can leverage for machine learning and artificial intelligence. So what exactly are these technologies? Well, many of the times these are optical systems such as Raman or near infrared. And the lasers in these systems interact with this complex biological soup in the bioreactors to get a molecular fingerprint that can be correlated to any number of process parameters. Other examples include technologies like capacitance, UV vis, refractive index, and even at-line HPLC skids. The craziest part of this story is that the FDA has been recommending that the industry adopt these technologies for over 2 decades. In October 2004, the FDA released a guidance document titled PAT, a framework for innovative pharmaceutical development, manufacturing, and quality assurance, where they encourage the industry to look seriously at these new technologies to help improve consistent product quality and right first time manufacturing. If you enjoyed this, be sure to give us a like and subscribe to hear more conversations around digital transformation and automation topics in the life sciences industry.